Oh, that's it.
Yeah,
Still interesting names?
we just did names, so
Oh, we did.
yeah,
Yeah.
very quickly.
Cool.
You're right.
Alright. So I'm going to be presenting a paper called Binders Unbound. And what is this paper about? This paper was in the ICFP, International Conference of Functional Programming, I think, in 2011. So it's a pretty good paper. And it goes through this concept about how do you implement variable binding? How do you, if you wanted to create your own programming language, a functional programming language obviously, or any other sort of structure that depends on syntax, then you're going to have to deal with variables. You're going to have to deal with names and passing these names to variables from different places. And a while back when I was sort of getting started figuring out how to develop the architect language for my company, I actually began with the theory of a lot of imperative sort of like the traditional, ever heard of the Dragon book? Like, yeah, that's where I began. And that had a really old way of doing, I guess, dealing with variables and use this thing called a symbol table and all that sort of stuff. But functional programming, we want to avoid mutation, we want to use trees, we want to make things persistent. So, and we generally like using algebraic data structures to represent constructions, such as a language, an expression language, or anything else. So how do we sort of deal with name binding or dealing with variable binding in this sort of field? And that's what the Unbound paper provides us a possibility of doing so in a very elegant way. So before we dive into this paper, we actually need to sort of have some background in another paper that sort of introduces some of the main concepts, because this paper is really about an implementation of the concept called locally nameless representation. So that's the thing that it's implementing. So this paper is not going to sort of explain to you what locally nameless representation is, but there's another one that I'm just going to quickly sort of go through, and this is going to give us sort of the necessary tools to then go back to the first paper. Is that okay?
Can you tell us what is locally nameless representation?
Oh yeah, this is what the paper is going to go through. So I'm going to explain it. So the first thing is we want to start with basically a expression language. Right. So we have an example of an expression language where imagine in your language all you had was the ability to sort of create a variable, the ability to abstract, create a lambda abstraction, or the ability to apply a lambda abstraction to another term of the same type. That's all you had in your language. And it basically says that the objects from this grammar are called raw terms because they're not isomorphic to lambda terms. For example, the two raw terms abs x bar x and abs y bar y, in this language, they would not be the same, but they're sort of they're equivalent in lambda calculus, which would be lambda x dot x or lambda y dot y, should be considered equal because the theory of lambda calculus identifies terms that are alpha equivalent. So hands up who doesn't understand that, because this sort of requires a little basic understanding of lambda calculus first.
Or at least the terminology.
Yes, terminology. Everybody's okay?
It's about, yeah, if you understand what a dummy variable is, that's the essence.
Okay. Right. So now, what this is, we'll go through will be like, okay, let's say if we want to actually try to get a bit more isomorphic to lambda terms, we need to create a quotient structure, and quotienting a set of raw terms with respect to alpha equivalence. And this construction is based on quotient. This corresponds very closely to the presentation of the standard textbooks on lambda calculus. So then it sort of starts introducing this other potential way of representing that same basic language of just having variables, a lambda abstraction, and the ability to apply lambda abstractions to other stuff. This introduces the thing called locally named representation. So it's closely related to the locally named representation, which has been extensively developed by McKenna and Pollock. This representation syntactically distinguishes between bound variables and free variables. So bound variables are represented by using a name, written x. Free variables are also called parameters, or are represented using other kinds of names, written p. Abstractions which always bind bound variables carry a bound variable name, and the grammar of locally named terms can be described as this. So I'm just going to give you an example of this. Suppose we start with a function, and in lambda calculus we use the lambda, and in Haskell we'll just use the backslash. Then when we have x, this is like a parameter to the function, then we might use x here. So maybe we do x plus 1, this is the body of the function. Then this variable here, when considered at this context, at the lambda abstraction, this is bound. So this would be a bound variable. Now, suppose we, instead of say x plus 1, it was x plus y. Right? Now, because y isn't present in the head of the lambda abstraction, then this is what we call a free variable. However, free variables eventually get bound anyway, because there's probably something on top that actually binds the y. And that's why we talk about locally, because it's contextual. Like, something might be free in this at this context, but then it becomes bound in a larger context. And this obviously captures a pretty common programming language systems. So
those that have lexical scope.
Sorry?
Those that have lexical scope.
Yes, those that have lexical scoping, yeah, which I think is pretty common nowadays. Then the alternative is dynamic scoping, but they have slightly different semantics here. So then, in order to extend that language, we then go from just having a var of x to having a b var of x or f var of x. And so by doing this, by constructing your language using these constructors, you can now not have any sort of confusion between something that is a bound name and something that's a free name. And that's important because later you're going to do operations on this structure. Operations such as optimization, if you want to transform your structure into a slightly different structure, or if you're trying to evaluate it, if you want to do substitution. All these things involve transforming that syntax tree until it turns into some result. So it's a bad idea to have something that you ambiguously don't know whether it's a bound variable or a free variable.
Just maybe mention that the bound and free have different. The variables are actually different types in there. It's an x.
Yeah, that's right. So that's a good point. The bound variable uses a type of x, and the free variable uses a type of p. This is sort of important in this sort of paper, but it becomes a little less important when we actually get to the implementation side.
So they're allowed to have different representations.
Yeah, they'll have slightly different representations, but then this gives us sort of like the simplicity to starting point.
Is it an existential type, or it's defined somewhat?
No, it's just like they just simply sort of like assume it to be a slightly different type. It could just be a type alias. If you were to implement this, you might say type p equal string, type x equals string. So they might end up being the same type.
But for all.
Sorry.
For all p, existential.
Yes.
It's not bounded.
Well, this is not even. There's no implementation at all. There's nothing constraining this or anything like that.
You think of this as a Haskell declaration. We've got data term equals bvar, term name, bound name, which is x. There's just some type in the scope which is that x, and through each of those comes a constructor. Yeah, like pointers.
some type, not for all.
Yeah, it's a subtype overall.
And T to T. So you could write this in Haskell if necessary.
So just with the example you done in purple, would why there be a free variable when we put into this?
Yeah, so this is sort of interesting because then this is sort of like the object syntax. Imagine if this was the actual programming language that you wanted to implement, but this is sort of like this is your compiler. This is your program that would be dealing with this language. So what you'd end up having to do to the entire pipeline, you'd have a parser that first parses and selects, and then eventually you construct a expression tree based on your constructors like this. And you're asking, when you finally construct this, would you construct this to be a bound variable or a free variable? Because in a way, like I said, this is a free variable in this context, but then at this context, it's actually a bound variable.
Yeah, that's what I'm
Right. So that question, the answer isn't that you use this or this. The answer is that you use something else entirely different that decides that decision for you. And there's a bunch of smart constructors and operators that would be. When I then go back to the Unbound paper, we'll show how to do that. But right now, like, you can see how this can sort of represent your action programming language, even though there's some ambiguity, as you can see. So it says that the drawback is that, again, not strictly speaking isomorph the lambda terms. Two terms may be alpha equivalent, but not syntactically equal, even though many results can be formalized using the unquotiented locally named representation. The construction of a quotient structure is required at some point for the sake of adequacy of the formalization. Oh, I just wanted to, because I have my own set of notes, because I'm going through the paper, but I also have my own set of notes here. And the locally nameless representation, the one that I just showed you is called the locally named representation. And so that's sort of like the beginning. But eventually we're going to call it, get to the locally nameless representation.
And it's so called because you've got local names, right?
Yeah. Oh, sorry, no, that's... So we go from locally named representation to De Bruijn, is that how you pronounce it?
De Bruijn.
De Bruijn
It's
representation. Okay.
If you can't say the sound, which I can't use it, just say drawing.
De Bruijn.
You can roll your R's.
sometimes I can't always do it.
Okay, so then it goes, okay, is this another approach to representing lambda terms? And using De Bruijn indices, we can build a data type that is isomorphic to the set of lambda terms. In this representation, abstractions do not mention any name, they are nameless, and each variable bears a natural number that indicates the number of abstractions to be passed by before reaching the abstraction to which the variable is bound. And more precisely, the variable marked with index I points to the I+1 enclosing abstraction. The grammar for the terms in the De Bruijn syntax, which appears next, includes variables built upon an index and nameless abstractions. So here it shows that if you want to represent something that is lambda x.x, you can then construct it instead just by using abstraction applied to var of 0. So in this case, when you actually have a bound variable, you don't really need to name it anymore. You can just sort of have a reference, a pointer that points to the level of abstraction that you're dealing with.
Like morally, but not literally.
So the key advantage of using indices is that no quotient structure is required. Moreover, no alpha renaming operation is ever needed when reasoning lambda terms.
So what exactly does it mean by quotient structure?
Quotient structure is this, when you quotient, you're sort of dividing by something in order to create something that's a bit more canonical. I actually...
Alpha equivalent, so lambda x dot x.
Oh, okay,
Divided
right.
by
So we're quotienting out.
quotienting
Yeah.
by the equivalence relation, which
Right,
is
okay.
doing all possible renames.
I see.
Yeah, so to reiterate, because I just realized that I understood that, but then I forgot. I just remember like what quotient sort of means in general. But basically, what are we talking about with regards to like canonical structure? So let's say you x dot x, right? And then you have y to y. Now, these are all legitimate lambda expressions. You can write a program and you write this and you write that. But as computers, they recognize these two things as the same thing, because if you evaluate this, it's just an identity, and if you evaluate this, it's an identity as well. So in lambda calculus theory, we have this concept called the alpha equivalence, which says that if you rename one of these expressions, say the y, and you rename it to x, then this expression should end up being the same as this expression, which is true. It's self-evident that is true. So what a quotient structure is to say, if we were to use this representation to represent these lambda expressions, there is some way we can sort of operate on the constructed term such that they all, something that's constructed in this way and something that's constructed this way can be essentially compared computationally. You can literally say, this is equal to this. In the computer itself, you can do something like, oh, term 1 equal term 2 somehow. And this is mechanically evaluated and will return true when term 1 and term 2 is equal under alpha equivalence.
So given this representation, just to confirm this, if the representations here, as in that var, ABST, those representations are the same, if and only if the terms are alpha equivalent?
Well,
Sorry, as in, yeah, so if you got, yeah, these, is this an equivalence relation as in these kind of, so if we got, like in this case here, x, y, that when you translate this representation, you get the same.
yes.
Same representation, but does that always hold? As in, are these things, if that representation is different, are the lambda terms different?
So the difference of the lambda calculus, the alpha equivalence is just one of the things you have to go and rename. And as humans we do it naturally. So then if you've got a computational system which is representing the lambda calculus, now you have to make the alpha equivalent work one way. So there's kind of these two approaches. So the named one, you say, I just get variables and the variables are going to stay the same, and I'm going to change the variable names. But now I have to find a way to make alpha equivalence work. And that's a tricky thing. And the alternative is De Broglie, where you, instead of that, you say, well, after each lambda, I'm just going to have my fresh name generator to make new variables. As it here, it's just going to do x1, x2, x3, x4 always. And then now the problem is you have, when you substitute, I think you're just coming to this. Now you have to renumber everything, and then that becomes computationally expensive. So there's a trade-off here. So I'm kind of stealing this thunder a bit. But
Yeah, so basically,
is that?
I was just writing, well, maybe I was, is if the De Broglie representations, if we've got two lambda expressions,
yeah,
to say A and B, the Broglie representation of A equals the Broglie representation of B if and only if A equals B. Is that a?
So you just got to just make sure you
That's
think
true or
about.
not?
So we've got our object language and
the meta language.
meta language. So we've got like the lambda calculus is what we're trying to
Yes.
implement. So
Yeah.
in that there is alpha equivalence is understood to hold, and we've got to make it hold in our model
So yeah, if we've got two lambda expressions that are alpha equivalent, I guess two questions. If we've got two lambda expressions that are alpha equivalent, are their De Broglie representations the same? And if we have two lambda expressions
Yes.
that aren't alpha equivalent,
Yes.
are their De Broglie representations not the same?
So what can happen is you might have two lambda expressions that are, from the perspective of lambda calculus theory, is alpha equivalent. However, when you implement them, the actual construction itself may look different.
The De Broglie representation may be different.
Well, locally named representation, the one we saw before.
Yes.
You could actually have completely
because that's from
different.
there, from the
Yeah,
board.
you could have completely different constructions.
Yeah.
I think what you're saying is does the De Broglie representation kind of solve alpha equivalence? And the answer is yes.
It does. Okay.
That's yeah. Strong.
So these are equivalent. Like if the De Broglie representations are different, then they're different lambda expressions. If the De Broglie representations are the same, then they're the same lambda expressions.
Just for this particular,
It solves the
problem.
alpha equivalence
Down to up, as in down to that variable renaming, which
You don't have to calculate it.
In doing that, we've made something else harder. So that's what
Okay.
he's just about to.
okay,
Like
okay.
using a regular expression.
So
Like using a regular expression.
It's just for this just this problem itself. Like there's a whole bunch of other transformations that like beta reduction like that also may be relevant, but just for this particular problem, De Bruyne representation will help us solve the alpha equivalence problem. So here it shows a example of a De Bruyne representation, and yep, so that's pretty simple. So as it says here, no alpha renaming operation is ever needed to reason about lambda terms. So the previous representation, the locally named representation, you need to actually have some function that converts them into this canonical structure that you can later say, okay, they're alpha equivalent. So there's almost like a precondition for doing any sort of operations on those terms. Whereas here, if you just straightforwardly use the De Bruyne representation, you don't need to have this extra alpha equivalence operation. The construction itself is naturally alpha equivalent. However, it suffers from one major drawback. The indices are very sensitive to the changes in the term in which they occur. In particular, De Bruyne terms involve a shifting operation which consists of incrementing in a term the value of all the indices that are greater than the given bound. Yep, that's the downside of this. And now we move to the locally nameless representation. Now, based on my just quick research, I think the locally nameless representation is invented by Arthur Chagouran. And I think that he's the actual guy who wrote this paper. So this is the idea where it was introduced. Okay.
So that thing, can you just kind of go through that difficulty of the De Bruyne representation? Why, this is maybe a short example of
Why it solves alpha equivalence?
no, what the problem was. There was a sentence that kind of I just didn't really get.
Yeah.
Oh, right.
I can do it summarize if you want.
Yeah.
So, sorry if I.
Yeah.
So the De Bruyne one, you say, okay, it's x0, x1, x2, but now you've also got so the lambda calculus, you've got abstraction, like introduce a function with the lambda, and the other one is application. So when you apply so you're substituting in, and what was your x0 is now put into a bigger context where it may not be x0 anymore. There's already an x0. So now it may be x37 because there's already 36 variables in that bigger context. So now you've got to go through and go, oh well, the x0 in the bit I'm substituting in goes to x37, x1 goes to x38, and renumber everything all the way through. Make sense? So you've got
In a very general sense, when you use De Bruyne indices, it ends up becoming really brittle because every time you need to refer to a bound variable, you're having a number. That number refers to a particular abstraction level. And then the problem is that if you change the term, the expression, by adding, I don't know, extra stuff or reducing things or something like that, these numbers are then essentially need to be shifted accordingly.
Okay.
And so it's like maintaining pointers. You now need to, every time you're changing the structure, now all these pointers need to be rewritten to point to something new somewhere else.
Essentially, we've got this tree-like structure, of course.
Yeah, so it's a tree-like structure.
And if we've got this let's say it's got 20 deep, and if we add something at like level 3,
Yeah.
anything that points to anything on that tree above that level 3,
Yeah.
from below it is going to muck up.
Yeah, exactly. So all those pointers need to be rewritten,
Okay.
and that adds a lot of overhead to
Yeah.
doing any sort of operation. Yeah, so, to give an example of what a De Bruyne representation would actually sort of look like, so here is a constant combinator. It's a lambda expression that takes an x and then takes a y and then returns to x. We call that a constant combinator. And then if you want to essentially turn that into a De Bruyne representation, it's sort of having just the lambda abstraction, and then 2, where 2 is how many abstractions are on top. So here x refers to the second position. So this would be the 1st position, and then this would be the 2nd position. And similarly, a substitution operation like lambda x to lambda y, lambda z, x applied to z, applied to y applied to z, you get these numbers again. So 1 refers to, so the z refers to z, so that's the 1th position. And then y refers to 1, 2. And then z here refers to the first position again, it's 1. And x refers to 1, 2, 3, 3, right? In order to index the variables, we always have to go from the deepest expression outwards, and so on and so forth. And if you think of this as a tree, it makes a bit more sense. So if you think of it as your lambda expression as a tree, then these numbers are indices into the tree level itself. Okay. So, like we said, De Broglie solves the alpha equivalence problem, but it introduces a bit of complexity now with having to shift those indices. So the locally nameless representation combines both the locally named representation plus the De Broglie representation into a new representation called locally nameless. And then this sort of gives us the best of both worlds. First, we get the alpha equivalence. At the same time, by using names to represent free variables, it avoids the need to shift De Broglie indices. And the grammar for locally nameless terms first involves a constructor for bound variables built upon the De Broglie index, and a constructor for free variables built upon the name. And then abstractions in De Broglie syntax are nameless, they do not carry any name. So therefore, now we can have, we get back sort of the bound variable and the free variable distinction, but the bound variable still uses indices, but the free variables actually use names. So lambda x dot x applied to y can be represented as abstraction and then application of the bound variable 0. So 0 here actually refers to 0. So sometimes, depending on how you sort of think of it, where you start at 0 or start at 1. Sometimes certain representations will start at 1, certain representations start at 0, but here 0 refers to here to this abstraction here, and the free variable y. And then that can be rewritten like that.
So it's a bit like tabs versus spaces. Why not both?
Yeah.
Like this.
Yeah.
Two warring factions, and then you say, well, we'll
Yeah.
do both. But it's actually, I guess, like evil mode.
Yeah.
You know, Vim and Emacs. Maybe it's actually a good idea.
Careful with the words.
So this representation solves the alpha equivalence problem and avoids the shifting problem, but it doesn't mean that this representation constrains to valid expressions. You can still construct an invalid expression. So he explains that an ABS B var 1 is an invalid expression because index 1 does not refer to any abstraction within a term, right? So
how does this continue to solve the alpha equivalence problem? Haven't we just brought back the same problem we've had before, because we've got these y's and things which are...
Because those are all free.
Exactly. But they're eventually bound up to tree.
No, because if you put them in another context, right, then you're going to have replacements. Right? But we're talking single expressions on their own, comparing them on their own. Right? So they're freestanding. Right? So it's free if the bounded variable is, if something is free, right, then it's free. So we're talking just this expression.
Let's name that.
Right. If you put it in another place, then you're going to bind it. Right? If it's getting bound, then you replace it.
Yeah, so I
With the
think
index.
That's
the
that's a
concept.
much more computationally cheaper operation now than it was with De Broglie, which is maybe not obvious.
The concept
Yeah.
that I think is that needs to be introduced is the context or the environment, what they call it, right? So you can only in a lambda expression, things are bound by the positional sort of argument. So like if x is argument to the lambda, then it's bound in the expression, and then a potential y that is just out there is free. But if you introduce it into a context, then the y is going to be bound to some actual value that lives in the environment.
How does that...
So what we've got is we don't have to renumber our free variables. So that gives us some manipulations will come for free.
So you don't have to do that first pass through the to kind of rename, right? Is that what you're saying? So that's
And alpha equivalence is kind of things like lambda x dot x, so it's bound. So you want in that case for the bound variables is where the drawing coach really shines, because you alpha equivalence for free. And
alpha equivalents mainly hit us in the free variables, but that's not obvious. So you need to work to see that's been fleshed out here. So this approach is quite clever because you kind of you build the strengths of both each of the places where it's best. Each one covers the deficiencies of the other one.
Okay.
You'll see how that sort of happens once we get into the next section. But I also wrote down a sort of like an evolution of how do you implement variable binding. You start with the raw representation, and then these are sort of like 3 points. Using raw terms are not isomorphic to lambda terms. Reasoning about lambda calculus cannot be formalized because you can't tell if 2 terms are alpha equivalent. You need to build a quotient structure. Then with locally named representation, bound variables and free variables are completely separated, can't be confused with each other. You never need to alpha convert bound names to avoid clashes with the free variables. Capture avoiding substitutions is simpler. Still not fully isomorphic, you still need an extra quotient structure. De Bruyne, no quotient structure, no alpha conversion. Requires shifting, hard to read. Locally names representation, no need for quotient structure. By using strings names for free variables, we don't need to shift De Bruyne indices. Free variable strings are called atoms. So the other people will usually refer to this concept as well. And atoms require a fresh name generator, so all names are always unique. And then atoms themselves are sort of actually just implemented as a counter, like an incremental counter, so that way you always get unique names. Okay, so once we understood the locally nameless representation, we can then talk about 2 important operations on locally nameless representations. One is opening, and opening converts the bound variables in an expression into free variables. Another is closing, and it converts free variables into bound variables. So suppose we have an expression constructed as abstraction t, which represents the lambda calculus term lambda x dot t. In order to investigate the body of this abstraction, we need to supply the fresh name x to open ABST. The variable opening operation can be written as t to the power of x, which is just here, in this example here. And what this means is that it is a copy of t where the variable name x that does not appear in t, because we want to avoid captures of other free variables, is substituted for every location inside t that refers to the bound variable in the ABS abstraction. So basically we replace a bound variable by specific free variables here. So an example is like this. If we have an abstraction of an application application bound var 0, bound var 1, bound var 0, opening this construction with a fresh name x means we convert bound var 1 here into free var x, and bound var 0 into free var x as well. To implement this open operation, we have to recursively traverse through this construction, keep track of the number of lambda abstractions that we are entering into, and whenever we meet like a bound var I, where I is equal to the number of abstractions enclosing the variable, it will get replaced with that fresh new free variable. We use the variable opening on a fully variable opening operation on a fully constructed binding representation in order to do substitution, which will eventually lead to evaluation. So the opening operation is necessary to do substitution, and substitution is necessary to evaluate these sort of things.
So once we introduce these free vars, we know we lose that De Bruyne nice equivalence thing where we're just comparing things structurally.
Well, at this point, if you are using the opening operation, it's like an actual function. The reason why you are using it is because at this point, you want to probably do a substitution. So basically, when you are using a locally nameless representation, if you want to substitute, which is necessary for the operation, the lambda calculus operation called beta reduction, then you need to use the open operation to convert that bound variable that is using the De Bruyne indices into a free variable, and then you can then go to every free variable and then replace those free variables with the value of x, if x was the free variable, right? And these two operations sometimes join together, as in like they literally compose, and then by composing they get this slightly different opening operation. So open operation here is just replace bound variables with free variables, the augmented opening operation, when the original opening is composed with the final substitution, is you just go straight from bound variables to term substitution. So you actually substitute it for the actual value that you want to utilize.
I don't usually interrupt like this, but I'm just mindful that we're now 6, maybe 7 pages into a 45-page paper, which isn't even the paper we want to read, and we've it's 45 minutes into, like, 2 hour session. We've 2 hours behind clock, so I don't know what the best way is to skim over this.
Yeah.
Or maybe we go to the original paper and then come back to this one to fill in the
So
gaps.
I've just got to finish the closing operation, and
Cool.
then we can.
And that's enough?
We can go. Yeah, we can
Cool.
go to the Unbound paper. And so the opposite is the closing operation, where you convert a free variable to a bound variable. And remember when I was telling you that there is another operation that sort of makes that decision on whether to use a bound variable or free variable construction. That's what the closing operation is for. The closing operation is used when you need to actually construct your expression tree. Yeah, so those are the 2 important operations, and that's the locally nameless representation. So now we're going to go back to the Unbound paper. Okay, so basically, the first introduction sort of describes why this is a good idea, why is this a good library. Now we finally get to the Unbound specification language. So it demonstrates the usage of an Unbound specification language in essentially what you might write for the purposes of implementing your language, right? So you have data E equals, data E, capital E is your expression, and then you have 3 possible construction. You have a var of n, a lambda, or in the previous paper was ABS, bind of n to E, and apply of E to E. Now, the 2 things that this library introduces is the name and the bind. And these 2 things are abstract types, which means that the library Unbound, of which I'm using the implementation here, Unbound generics, there was an original implementation, but that was a fork that later got updated. It means that they actually do export the actual constructors for these abstract types, but you're not meant to use them. You're meant to be using smart constructors to actually create these things. So the name here allows us to basically say what things are actual variable names. And so what it says here is just any E can be like a name, but we're probably later limited to particular strings or something like that. And then the bind is used in the lambda abstraction to allow us to represent bound variables. And what happens is that when you actually use the constructor, the smart constructor, to create bind, it actually introduces just only free variables. And I just need to show you how the bind actually is defined. So we go into Unbound generics, locally nameless bind, and it has data bind
Might want to
PT.
just make it a little bit bigger.
So this is a bind P of T, and both P and T are instances of the alpha type class. So if we go back to the paper, it gives us bind of N and E. So both names and the expression that you're binding them to is going to be part of this alpha type class that is defined in the library. And then we have to look at name as well. So the data name A has 2 constructors. One is the free name, and then another one is the bound name. So you can see that the free name is string, and the bound name has an integer, which is the index into the abstraction. The smart constructors for creating values of the name type are these three functions. One is string to name, another is s to n, and another one's make name. And if you look at the source, they always end up using fn instead of bn. So here it is make name fn. So at no point can you actually deliberately create a bound name. You always start off with free names. And what happens is that in the process of constructing your tree, you use these smart constructors to then automatically convert certain free names into bound names. So we can go proceed from there. Okay. So it gives a sort of an example here of the operations that actually introduce binding. So the bind operation takes a name, the expression, and returns you a bind of n and e. And this bind operation is actually what uses the close operation we talked about earlier. Because the close operation converts free names into bound names. And like I said, you can't ever actually directly just create a bound name. You have to use these. You have to use this bind function when you're constructing your expression tree to actually convert some of your free names, the eligible free names, into bound names. So that sort of answers your question?
So that bind operation, I see use that on part of a tree if you want to, you don't use it in the whole tree.
So every time as you construct your expression tree, like let's say you're parsing your language and you're sort of building up your expression tree, you're going to be using that bind every time you see a lambda abstraction. So you go, okay, this is lambda abstraction, I need to be binding something, so you run the bind function. And if you sort of roll back, if you go back to what happened before that happened, you would have used like a make name or one of the other name constructors that would have always constructed fn, which is free name, because it doesn't know if it's actually bound.
Okay.
Like you don't know, when you first use a variable, when you're writing your lambda body, you actually don't know where it's actually going to be bound. At least the computer doesn't know where it's going to be bound. So it has to first start off with free name, and then as it kind of goes out and builds up that tree, it's going to know at what point a certain free name is actually going to be bound, and that's why you use this bind function. So it's always like incrementally going, all right, I'm going to go back into the tree and convert them into bound names. And then I'm going to go up. Oh, so there's another abstraction. Now I'm going to go back into the tree. It's like you build up the tree, but every time you build another layer of the tree, you're going into the tree to convert things, and you're going back out. Yeah.
So for example, go back to this purple one, the x, y on the board. If we just did the x plus y is free. So once we bind the y on top, we traverse back down and make y now bind using the Brewer representation instead of the free variable representation, because
Yeah.
we're bounded.
So this would start. Both of these things would start off as fn.
Okay, and then we add x that we
And then when
bind.
you did this, you would have used the bind operation, which would have converted this into a bn. And then when you get up to here, it would go back into the system and then convert this into bn.
Yeah, and we can do that fairly quickly because we've got some sort of map going on the inside that we poke out and work out. We don't need to search the whole tree every time we do this, do we?
I assume so. I didn't
Yeah.
go
Okay,
further than that.
they're saying, yeah, smart. Okay, cool.
It certainly seems like you've got enough information to be able to maintain a faster access structure.
Yeah, okay,
You
yeah.
can skip the bits you don't need.
So just remember that this bind operation uses it really refers back to the original paper, because the original paper introduces the two fundamental operations, opening and closing, and bind makes use of the closing. And there's also unbind, which goes the opposite direction, and it has this constraint called fresh. This is actually quite cool because in the previous paper, it will later start introducing things like theorem properties on this representation in order to prove certain things about it. And in order to implement one of these sort of constraints on these proofs, the implementation makes use of monads that do that. Monads and type class constraints. So a monad in Haskell is implemented as a type class, and this type class is called the fresh. And as long as these operations exist within the fresh type class, it actually maintains that constraint. So this is the fresh constraint, which we'll get into a little bit later. FV is a free variable operation. You give it an expression, it gives you a set of free names that are inside that expression. And then there's also the substitution operator that takes a name, takes an expression, gives you back that a new expression that has that name substituted into it. Okay, let's keep going beyond that. So that original example shows us how we can just bind one name. And what this library is trying to show in this section 3 is trying to show how you can use this representation to do more sophisticated forms of bindings. So rather than just binding a single variable, what if we could bind multiple variables at the same time? Now, in lambda calculus perspective, binding multiple variables can be sort of represented in either two ways. One is you're just sort of like chaining it up, you're just doing lambda x to lambda y to lambda z. You can also represent it as a tuple of some sort, so you x, y, z is a single construction here. This has got nothing to do with
That's
that.
carrying. Right?
Sorry?
That's carrying.
Yeah. What this at this part point in the paper, it's not actually talking about that at all. It doesn't care about whether you're wanting to represent tuple or something else. It's more kind of saying, suppose you have this in your syntax, like you have the ability to go lambda x space y space z in your object language that you're implementing. How would we be able to represent that in our underlying implementation? So it generalizes really easily. Rather than just binding n to e, now it binds a list of n to e. And this is because if we go back to the definition of bind, you can see that it's fairly generic, and that's why this whole thing is called unbound generics, right? The type that it's binding is just p. P is just any pattern, and patterns in this case are any instance of the alpha type class. So the alpha type class is introduced in the alpha module. And this is how it sort of, it uses a lot of type classes in order to make all of these things super generic. So this is the alpha type class, and then if we go to the instances, it supplies a bunch of default instances, like Boolean is an instance of alpha and so on and so forth. But then anything that is alpha, then a list of the thing is also an alpha as well. So that gives us the ability to represent multiple variable bindings.
Just to make sure that I understand correctly, the reason that type class is called alpha is because here are things that can be shown to be alpha equivalent.
Yes, yeah, that's right. And that's how a lot of these operations that essentially require that alpha equivalence to actually work, by putting them under the alpha type class, essentially means that you can only use these operations if the things that you are operating on are alpha equivalent. Okay, so then it sort of introduces, suppose we want to represent another kind of aspect of language, like let x equal e1 in e2, which is a fairly common expression in Haskell, right? And you can make use of this pretty easily as well. You just do, okay. Well, what it does is it introduces an extra combinator here, which is called embed. So now you do something like let's bind a tuple of the name and the embed of E1 into E2. And that allows us to basically put the value of the n on the right side. Again, because it's all generic, right? The P just has to be an instance of alpha type class, and a tuple of the name with the embed constructor of E2 is also an instance of the alpha type class. And then we can proceed to do more than just one let x equal e in e. You can just generalize it again and make it a list. Suppose we want to do something like nested binding, where we want to do something like let x equal e1, comma x2 equal e2, comma so on and so forth, where the bindings in the beginning are bound in all subsequent bindings as well. So you can write something like, let's see, I can find it. Let's write it down here. So here, the x equals 1 binding becomes available here, and then this binding becomes available here. So this is they call it this nested binding. And in order to introduce this, we just basically introduce a new constructor called rebind. So therefore, you can then use, hold on, should be in the next paper, next up, something like this. Data E equals let star of bind lets of E, where lets is a list, could be an empty list, or a cons of the rebind within embed E lets. And this is recursive. What does the rebind do exactly? It actually explains it slightly before.
So that's equivalent to just a list of.
It's a list of bindings. The reason why they introduce a new constructor and not just use the existing constructor is because the binder is meant to sort of scope the E. So let the N bind N in E ensures that N only exists or it becomes available in that E. And what we want to do here is we want to be able to say bind this name and then make it available in this next expression, which also includes another binding for a name to the next expression. And that would essentially blow up a sort of a nested structure. So it says like, Unbound provides a novel rebinding pattern company for precisely this purpose. Rebind P1 of P2 acts like a pattern type tuple of P1 and P2, except P1 also scopes over P2. So binders in P1 may be referred to by terms embedded within P2. The fact that P1 scopes over P2 in this way has no effect on the pattern portion of P2. For example, consider the specification type N1 is equal to the name of E, type N2 is equal to the name of E. Bind, so this is the actual entire binding. Rebind of N1 with given a tuple of N2 embed E1. Here N1 and N2 are bound in E2, and additionally N1 itself is also bound within E1. So that's why when we see this rebind, this is the first parameter of rebind, and then this is the second parameter of the rebind. So rebind allows you to sort of recursively create this structure, and then just basically ensures that names in the front allows you to be used in subsequent bindings as well. However, this ends up being generalized even further, because if we can do that, then we can also do recursive binding. So recursive binding is exactly the same thing as what was shown prior, but now you can also say something like, suppose this was not thing, then you can say something like x plus z. So now this becomes available here. So in many languages, you often have this sort of thing where at a certain level, every single binding is available to use in other bindings. So it doesn't become linear anymore. This tends to be quite useful because you can sort of reorder your code in arbitrary ways. And because sometimes you'll find yourself finding yourself needing to sort of define some sort of value at the top level, but then have sort of like the sub-expressions being defined underneath it. And that's sometimes quite natural. In other cases, like if you use languages that really have no ability of sort of being self-referential in this way, you end up having to always define your sub-expressions at the top, the 1, 2, 3, and then define your final expression at the bottom of the, say, your programming language file, your module, or something like that.
And if they mutually refer to each other, then you're in trouble.
Yes, exactly. So that's an extra sort of disadvantage if you don't have that ability. So
I just want to call out as a special item of shame, Scala, which whether or not you can call things defined further down in the file depends on the evaluation of that term. So if it's by value, then you can't, and if it's by name, then you can.
Oh,
It's even
yeah.
worse. It's even worse.
So
You
because
can't-
of many bugs, and it's because of they wanted to make it close to the JVM and Java, so yeah, if you got a def, you can, and you want a val, well, the compiler accepts it, but then it'll null point it.
So this is,
Yeah.
this is for nice performance on the JVM or nice mapping to the JVM's instructions?
No, no.
Less compiler work to make it match, so it's the closer encoding of the.
Right.
Yeah, I call it a linked abstraction.
It makes the implementation simpler
I think so.
at the cost of losing that functionality.
Yeah, and confusing a lot of you lose both scalars and all null state from there. Other variables.
So-
Sorry, I've now derailed.
No. Just that example on the board with the X, Y, Z. I noticed you rubbed out the Y for the Z equals.
Yes.
If we kept the Y in there, that would be sort of valid Pascal, but can we represent that here? Well, it wouldn't, it went round to break, but it would still be valid. I'll get Y plus, can we represent that in this sort of form? Where we've got sort of a looping.
Yeah, no, you totally can. It's just like, I mean, this doesn't prevent you from creating an infinite loop. If you tried to evaluate this, you would result in infinite loop, but it doesn't mean you couldn't create it.
Yeah, okay.
You could definitely construct this.
I know in this case, but there's some cases where you could have recursive bindings in Pascal which do evaluate something
Yeah, exactly.
reasonable.
Just like when you might have what is something like, something even and something odd, you always have some sort of termination case that eventually terminates down to, but this allows us to refer back to it easily. Here it's there's no termination case, I'm just constantly adding things, it's just gonna be constantly adding further. So, how do we represent recursive bindings? So, it just introduces a whole nother constructor, this time called the rec one. It does mention something about rebind though, because we use a rebind prior to just create that sort of linear scoping of it. So rebind doesn't help because it forces us to separate binders from the terms over which they scope, just like bind. We need to be able to freely mix patterns and terms bound by the patterns in the same data structure. And Unbound provides the rec combinator for this purpose. In rec P, the names of the pattern P scope recursively over any terms embedded in P itself. However, rec P is itself a pattern, so names in P also scope over any term that binds rec P. Intuitively, rec is just a recursive version of rebind. So then you can then implement that recursive let just by saying bind of this thing over E, where this thing is a rec of a list of a tuple of n and comma embed of E. And then of course everything inside this scopes over itself. Hence all the names are bound in all the definitions as well as over the body as well. So that's just because X, Y, and Z can be used by any one of them here, but then also it gets used here as well.
It's like if you were trying to do a camel, you'd use this just inside a let rec. If you're trying to do Haskell, then you need, like, all definitions bindings can potentially be mutually recursive with something, so everything would have to be using rec.
That's right. So cool. That's basically the main sort of constructors that this library gives you, and then the rest of the library is basically a bunch of operations over using these fundamental constructors to create an expression system. And then it goes into the close and open operation again, and we'll see that as well. This actual section, I think it's called section 4.1. It's going to talk a little bit more about how the name thing actually works. So prior to this, we talked about the locally nameless representation where you can use the indices to represent your bound variables, but then you still keep your free names for the free variables. So this goes into a bit more detail about that. So how much time we got? It's about 8 or 9.
About 2 hours.
Sorry?
Until 10.
Okay.
You might have to say.
The room is booked until 10.
Right.
Yeah, and at some point they're gonna also take the food if you guys wanna just take a quick break and finish up.
Yeah, that's good.
I don't need to be asked more than twice.
assumptions in Scala you mentioned is one of the least my least favorite things in Scala. I really hate it. I got so disappointed when I saw this first time.
Yeah. Eventually we become immune to it.
Yeah.
Yeah. Still trips off the experience.
Okay, so you've been working with SBT lately? No, that doesn't
Yeah, I simultaneously hugely admire SBT and hate it. It does more than a lot of other build tools.
But at the cost of,
Sanity.
a very complex model.
Most of the time, it's the little things.
Sign the paper to do with
So, one of them is trivial. Like I love the watch.
Well, they didn't give me one.
Watch. You can watch any
But they didn't give me
build
one.
expression.
Good question.
But there's a small bug in
I
its
just do what they
algorithm.
don't.
So when you go, oh, okay, that's enough watching. I don't want to run my test another time. I'll stop it. And you press any key to stop, and then do it one more time first. So if you really don't want to do it, you have to kill it. Which used to kill SVT. I don't know.
Yeah, I use SBT every day, so I don't have this experience to coming back to being disappointed again.
Yeah, I've been griping about it a long time, but I've never actually raised it to our role that contributed, so we shouldn't.
I just have got this SBT code base. Terrible.
Good stuff.
It's because there's a lot going on, there's a lot of macros.
Yeah.
Where?
The language it uses just drives me crazy.
Was that one?
The Scala, not
HVG uses a lot of macros.
Oh.
It tries really hard to make things magically just work. That's maybe
And it very
It cuts down
not
on the-
magically makes it fail, right?
when the cases where you don't, in the edge case, then you're royally fucked. Yeah, it did cut down on the perceived complexity. Like it used to, like getting it when you gotta get more terms now. Build. Anything. Anyway, when you're getting a value from a build task or setting, I think both of them have values and it's easy to do dot value. So you've got a two-level thing, the setting and then the value that it has or produce a task, the value that it produces. So now you can just kind of magically access it. And that's kind of doing clever macro things to kind of magical term rewriting, somewhat similar to this actually. Kind of with part of me says just make it explicit that even if it becomes a bit more complex, at least that it's easy to understand.
Okay, so let's start again. Okay, so section 4.1 is basically going to go through what we sort of went through in the previous paper, but in relation to the actual, how it sort of implements those So in a locally named representation of terms of binding structure, it separates bound variables represented by de Broglie indices and free variables represented by atoms. Now, atoms are often taken to be strings, but any countably infinite set with decidable equality will do as well. The representation has an advantage of that alpha equivalence is simply structural equality. Distinguishing bound variables and free variables in this way also means that we do not need to keep track of the current scope of the free variable and shift it as we move from one scope to another, as we would have to do with a de Broglie index representation. The locally nameless syntax we use to represent terms with binding structure is shown in figure 3 as in figure 2. We separate terms from patterns. Terms T have the type capital T, whereas patterns have pattern types capital P. Names that appear in terms can either be free names. This multiply operator. I actually didn't quite understand what that multiply operator was.
It's X.
It's just X, just random X. Bound names B.
Which are in different fonts.
Okay.
Just,
Free names are drawn from the set of capital A atoms. In an interest of simplicity, semantics here we describe only the single sort of atoms or the multiple sort of atoms. Straightforward. Terms also include applications of constructor constants k to 0 or more subterms. Constructor application covers all terms of some regular type R. In the semantics, they are all handled in precisely the same way. And then
regular type is
yeah.
Leave the digression to go into.
So like terms and patterns can be formed in an application of constructor subpatterns. Names inside the patterns are binders, written -x, which represent a binding occurrences of names. We denote binders with special syntax to emphasize that we should think of them as placeholders with an associated name. The astute reader may note that we are punning a bit with our syntax. Bind and friend show up as types, whereas they're playing the role of data. The resolution of the apparent inconsistency is that bind, embed, rebind, rec are all singleton types with eponymous constructors. For example, we define an operation that lists all the atoms that a pattern will bind to. So binders will give us a P and then a list of atoms, and then its implementation is fairly straightforward.
So I guess singleton types with eponymous constructor is the fancy way of saying that the usual Haskell thing of data x equals x, something. The constructor is named the same as the type.
I'm not really sure. I actually don't know if that's actually true in the Unbound generics, if they did the same thing that way. Say, for example, here is rebind, and if we look at the constructors for rebind, oh, well, there you go.
That's spelled different.
RE, but it's B and D. Okay. So, even though we're using Haskell-like syntax, this definition is type-directed. It works for any pattern type. And then so on. Bound names B consists of two natural number indices, J at K. The first index, J, references a pattern counting outwards from 0. The second index, K, is the offset. It references a particular binder within a given pattern, counting from left to right. Also starting from 0. For example, bind -x, -y, -z, and then bind -q, 1 at 2. This thing here. This bound variable, 1 at 2, refers to the -z, the index 2 binder within the index 1 enclosing pattern. So that's 0, 1, 2, but then 1 here means 0, 1. This is the 1th enclosing pattern, and this is the second binding.
So remind me what A
think
is
it's
an atom,
Yeah,
right?
I think it's important to have a look back to the bind constructor to see that it wasn't just a single number. It was sorry, not the bind constructor. So you do bind P, and P can be an N of something of an N, where N is the name of a thing. So we actually want to look at the name source here. Do you see how a bound name is actually 2 integers? So it's the binding level and the pattern index here. Whereas here it's saying, suppose you just set 2 numbers here. You have to be able to find which pattern that we're going to be utilizing, and also which specific variable inside that pattern we want to be using. I think that's because you can generalize to different kind of patterns, like patterns of lists, where you can have multiple things being bound. That's how I interpret it, in a way. Therefore, an important part of the representation is the connection between patterns and offsets. We make this connection precise with the operations int and find when we make the definition. So take a pattern, take a natural number, and you get a maybe of an atom. Or you take the pattern, the atom, and you get a maybe of a natural number. So env takes a pattern, a natural number n, and finds the nth name bound in that pattern. And failing, if there are not enough binders, find takes a pattern and a name and finds the first index of that name in the pattern, failing if the name does not occur. So that's, I think, all to do with the whole pattern structure that you have inside bind, because you always go bind p, where p is the pattern, and then whatever is the thing that you're binding will be available to be used in. And in this case, the p here is sort of becoming a bit more general, not just a single binding, but any number of potential bindings, which is why then things that refer to those bindings, the actual bound variables, need to have some way of referring back to where inside this pattern. First, which pattern are we talking about? So that would probably be something like which lambda abstraction level that we were referring to. But then within that lambda abstraction level, which specific variable that which specific binder, as it says, in that lambda abstraction that it's referring to. That's why there's two numbers. Okay, so now we have the close and open operation. As we discussed previously, they do basically the same as what we talked about. So it talks about here where he says, define a version of close for patterns, close of P, whose job is to recurse for the patterns looking for embedded terms to which close can be applied. And when recursing under a binder, bind, rebind, or rec, both close and close P increment the current level. So because this library has introduced these extra sort of constructors, not just bind, but also rebind and rec, they also need slightly more augmented operations as well to do closing. And then open does something similar, and then of course there's also the pattern version called open P. And then so on and so forth. So if we want to construct an expression, figure 5 lists the smart constructor destructors that are exported by Unbound to be used. And that's all this sort of stuff. So like I said, you never actually directly use the constructors for like name and bind. You always use the smart constructors. This is a list of both the open and close, but then on figure 5 is also a list of the other things that you use. So if you want to construct a free name, you use the string to name to string. If you want to then construct a lambda abstraction, you use the lam, whatever the lam in your language is, but then you would also use the bind operation. And then if you want to use rebind, use rebind. If you want to do recursive bindings, you use rec. And then if you want to be able to say let x equal something in something else, you have to use the embed. You never use the capital embed, you always use these small embeds. And this is an implementation for open and close. Okay, let's get to this freshening and unbinding. So this is something that we didn't talk about in the previous paper, but the previous paper also sort of talks a little bit about it. But here's something that gets a bit tricky. So once you've constructed your expression tree, you then need to operate on it. And when you operate on it, such as, for example, substitution, evaluation, optimization, and stuff like that, you need to do the opposite of what you did in order to construct the tree. So for example, you might want to do unbinding. So it says, given a term bind P of T, it is only safe to call open P of T if none of the binding variables of P clash with the existing free variables in T. Therefore, before opening, we must first freshen P by assigning a suitably fresh name to its binders. At this point, we leave the precise meaning of suitably fresh to an interpretation, and then concrete implementations are discussed. I did actually have a look at the implementation. It just seems like they just increment a number, and then they get another fresh name, and just append that number to whatever it is. We omit the formal definition of freshening, blah, blah, blah. We can define unbind as an operation that freshens the binding variables in the pattern and then opens the body of the binder with a new pattern. So unbind takes the bind P of T, take the P, freshen it, give you P prime, and then return the P prime, and then open P prime of T. So this is these are the names. This is the thing that the name is available in. You need to freshen those names such that you can then open it. And what is open though? It converts the bound variables into free variables. In contrast, the destructors for rebind and rec do not freshen before opening the rest of the pattern. Instead, they use the pre-existing names. Why do we do this? When opening a bind, we must generate fresh names for its binders. By the time we come to opening a nested binding, fresh names will already have been chosen for its binders when enclosing bind was opened. Hence, there's no need to choose new names. In fact, we must not choose fresh names, since there may exist corresponding free variables over which we have no control. For example, consider the term bind, rebind, P1, PT, P1, P2, T, in which T may contain references to binders in P1. If we use the unbind to take apart rebind P1, P2, and T prime, there will now be free variables in T prime which will match the names in the binders P1. Freshening again when opening a rebind would destroy this connection, and in particular would mean that we could not reassemble the original term using rebind and bind. This is also why we must have bind and rebind as distinct combinators. If we use bind everywhere, unbind would have no way of knowing whether it was opening a top-level bind, which must be first freshened, or a nested one, which must not be. Does that sort of make sense?
You can't rename something if it's used elsewhere and you don't have control over that.
Yeah. That's basically it. Then a final payoff in our representation, as we finally specified the basic operations: alpha equivalence, free variable calculation, and capture avoiding substitution. Alpha equivalence relation on terms is defined mutually with the notion of equivalence for patterns, which ignores binders and checks that embedded terms are alpha equivalent. This alpha equivalence relation is essentially structural equality. The only reason it is not precisely structural equality is that the name annotations on binders are ignored in PEQ binder. Actually, I'm not entirely sure what that specifically refers to, but there you go. You can compute free variables very easily. Free variable and bound variable are distinguished syntactically, so then you just recurse through and you just gather up your list of free variables.
So that's a common thing that's computational.
Yeah, apparently. And then when we define substitution to terms of patterns, we see that the free variable we substitute for, we replace it with the term being substituted, otherwise we simply recurse. So that's very simple as well. We need to do nothing special when recursing for binders because since free and bound variables are distinguished syntactically, we're in no danger of mistaking a bound variable for a free variable we should substitute for, or of accidentally capturing any free variables in the substituted term. Okay, so locally closure. This is sort of the proof part. Like, how do we prove that this all the stuff makes sense? Let me see if I actually have. I think I have some notes on this. Okay, the locally nameless representation allows for the possibility of constructions that do not correspond to any valid lambda calculus term. So we have this concept called locally closed and local closure. Our terms which are locally closed, and that means there are no dangling bound variables. So we saw that example in the previous paper where it says abstraction bvar1, that's an invalid lambda term because it's referring to something that doesn't exist. And then therefore we need to have this operation called locally closed, which is as much a predicate as much as an operation. Because it's sort of saying, is this actual expression locally closed? That makes it a valid expression. For example, ABS3 is an invalid locally nameless representation. It's also possible to create a locally closed predicate, which is a recursive implementation. Basically, why is this important? Because operations, all of our operations, whether it's a substitution or opening, closing, binding, unbinding, rebinding, all that sort of stuff, they need to preserve the locally closed property. So if a term is locally closed, if we apply those operations to that locally closed term, it needs to return back a term that's also still locally closed. Because if it doesn't, then we've done something wrong. We essentially have an operation that has taken something that might be a valid lambda term and produced something that is not a valid lambda term. So here it says, by making the type combinators of our library abstract and making sure that you use the smart constructors, the central property of this interface, the invariant that it maintains, is that users of the library can only construct locally closed patterns and terms. And so that's a good thing, right? Because it sort of like saves us a bit of mental overhead to making sure we're doing the right thing, which is the whole reason of using things like Haskell for our type safety purposes. In this case, it maintains a locally closed invariant. And so these are a bunch of theorems. Would you guys like to go through theorems itself, or is this because this sort of just goes through and just proves it, or would you just prefer to just trust that this library actually does work?
Maybe just talk very quickly about what the kind of basic idea is.
Okay.
Or do one case or.
Oh yeah, right. Okay. This previous paper actually sort of goes through a bit easily, and because the other paper sort of describes the same thing. So it says something like, this is the LC var prime rule. It is self-evident that free var x is locally closed. If
Because you're only interested in bound variables that don't make sense.
Yeah,
that
exactly.
Come from nowhere.
So this is a thing called if T1 is locally closed, T2 is locally closed, then the combination of them is also locally closed.
An application.
Application of them. Abstraction as well. So here it's sort of saying if you open the T with X, so if you do an opening operation, you open that term. So you open the term has some sort of abstraction, and you're opening it with X. So you're replacing some of the bound variables for a free variable, which will be X. And if that is locally closed, then it should still be locally closed if you also abstract that T again as well. And this is actually quite similar. In practice, we use a slightly different rule to deal with abstractions. LZ var prime holding true for one X. Yeah. Okay, those are some locally closed rules. And it also describes a little bit about how you might implement it. So you might have an operation, a predicate like LC at, which should return true if it is locally closed at a particular k. And suppose you had v var I, f var x, then you just do this sort of stuff. Like, is the index of the bound variable less than the k that you're in? If it is, then it's true. Free variables are always locally closed, and application you have to be locally closed in term 1 and locally closed at term 2 at the same k. And then abstraction means you increase the counter for because you're entering into an abstraction. You just leave locally closed at t as well. So it's a fairly simple thing as well. And then there's a few other things like there's a predicate like body, and it asserts that T describes a body of a locally closed abstraction. The definition is equivalent to the premise of the rule locally closed abstraction that defines locally closed abstractions. So there exists a L for all X not a member of that L. If you open that T with that X, it is locally closed. This is a bit strange because at this point it never actually explains what L is, but I think L is actually.
Afraid to ask.
Yeah, well, I think the L here actually means it's all the names that already exist in T. I think that's what it means.
So we consider that an abstraction is locally closed if there exists a finite set of names L, such that for names not in L, for any name X not in L, the term T superscript X is locally closed.
Were you reading that?
It's,
This is the
just
the previous paper.
above where you were
Section
in the
3.4.
Shagarad. Yeah, it's a set of names.
Yeah, it's like some set of names where the name that you're trying to open with is not that set. The problem I had with this was like, why does that set matter? I can only imagine that only matters if that set is the set of names that is being used in T already.
It seems like it's a kind of proof mechanism kind of at this stage. So yeah, it's proof by induction on the length, the index of the bound variable that may or may not be closed.
Yeah. So it has basically the same stuff, same set of rules in the ICFP paper as well, with the LC3 sort of LC var, and it's also going to extend those rules to its own special constructors like rebind, embed, and rec. It's all pretty straightforward. Freshening preserves local closure. If LCP, then freshen P to P prime, then LCP prime. this is a reflexivity, symmetry, transitivity can be established by straightforward induction. Free variable also respects alpha equivalence. So if T1 is equal to T2, then FV of T1 is equal to FV of T2. So I think this is alpha equivalence. I remember this operator actually means alpha equivalence. So if the alpha equivalent, then it makes sense that the free variables of T1 should be equal to free variables of T2. And substitution respects alpha equivalence. If T1 and T2 are alpha equivalent, and S1 and S2 are alpha equivalent, then the substitution in T1 should be alpha equivalent to the substitution in T2, with S1 the one substitution.
So that's a kind of capture avoiding substitution.
Yes, capture avoiding substitution.
So if they do, what could go wrong is a bound X. Oh no. In a general case, if you rename a bound variable and it breaks, but
when you do a substitution, you have to first open the expression.
Yeah, in this that doesn't make sense in this context, right? What I said.
Yeah. So you have to convert your bound variable to a free variable. But when you do it, you've got to make sure that your free variable doesn't conflict with any other free variables that are being currently used in that expression. Because if it does, then when you do the substitution, you're then substituting for things that shouldn't have been substituted. So you could do this very naively by, I don't know, just creating, just checking if you're conflicting with things. But there's no point in doing that if you have a way to simply create always a unique name. So that's what the freshen part is for. So that way you always get a new name, so you never conflict with anything that's inside the existing expression. But a little bit of complexity here is that you have to be careful because the thing that you're substituting also shouldn't be conflicting with the other three names as well. Because if you do, then you're now saying, if say for example, the expression that I'm going to substitute in makes use of the variable x, but then the thing I'm substituting into it also makes use of x, but it's a different x, that's a problem as well. So you also need to sort of, when you actually do the substitution of that thing that also contains x, you might want to actually rename that. So it would have been bound already, so you would have so the two uses of freshen would never create the same set of names. So you got to make sure the thing going in, the thing being substituted, is also unique, as well as the thing being substituted into.
Definitely, if you're naively rolling your own lambda calculus, you get this wrong. In my case, time after time after time. Like it's not never quite right. Never done it to example.
So then it states, the first theorem states that the interaction between bindings and alpha equivalents. It states that two bindings are alpha equivalent when we can freshen two patterns to the same new result, and then show that the bodies are alpha equivalent under consistent renaming. And then pi1 and pi2 are permutations, and by freshen, pi1.t1 is the application of permutation to a term. And then now we have some freshen theorems. So if you freshen p1 to pi1, and freshen p2 gives you pi2, and pi1.t1 is alpha equivalent to pi2.t2. Then bind of p1 t1 is alpha equivalent to bind p2 and t2. I'm not entirely sure what that theorem is saying. Anyway, we can move on. Now in section 6 we start talking about the actual implementation. So the only thing sort of interesting about this is that it makes use of type classes. So it says that, so in this particular paper it describes the original implementation of Unbound. The new implementation of Unbound is actually works. We had actually tried using the previous implementation and there's all sorts of problems. The new implementation works better. So I don't think it actually makes use of things like template Haskell or anything like that, so you don't need to use template Haskell anymore.
Do you know anything about why the original implementation didn't work?
I'm not entirely sure because it wasn't myself necessarily working with it, it was one of my team members. We tried it and then I was like, oh, try this library instead, and then that ended up working.
Sorry, what didn't work?
The
Well,
original.
so the original implementation of Unbound as per the paper. didn't work for some reason.
It's much
It
more
hasn't been
modern.
updated for a long time.
Yeah.
So the average GHC might have, the language might have changed.
Yeah, I don't.
It's been a while. Yeah. Yeah, the original package is called Unbound,
Use GHC 8, I think.
and the new one uses it's called Unbound Generics. I think it's actually it sort of explains what is actually different. And the front, this is an independent re-implementation of Unbound, but uses GHC generics instead of REPL-lib. So that's better because it's actually making it the native generic system.
I guess the fact that they used Replit, it kind of shows you something that age of it.
Okay, so then basically all the operations are separated between different modules, which are at the end of the day different type classes as well. And then the reason why generics here is important is because you want to be able to sort of automatically derive that your expression tree is alpha as well. And that here was sort of done through the sort of template Haskell stuff, but in the new system you don't actually need that. You just sort of need to derive GHC generics, and that sort of works. So if your expression tree can derive the generics, then that becomes an instance of alpha. So that's quite nice. There's also a substitution type class which contains the actual substitution operations as well, and then that's here as well. There. And the key point about this is that it's about types that can participate in capture and avoiding substitution. And you get the subst function here takes the name of B and the B itself, and then the A, and then returns the A. So this would be your expression type, and then this would be the things that you consider to be names. Sorry, this is not the things that you consider to be names. These are the types of the things that are named. So a name of B would be some name that is of type B. So then you have to give it the value of type B, and then your expression will then be replace that name of that type B.
Name B is the symbol, which
Yeah,
is going to
with
be
the symbol, with the
bound
actual value of B. So you can use this for. I'm assuming that you can use this for actual type safe programming, but I don't think this necessarily is about type safety in your object language. I think this is about, like, suppose you have a particular kind of name, particular kind of particular kind of atom.
Yeah.
Yeah.
So I guess if you're keeping types at this level, then does it work if B itself has type parameters?
Yeah, so I don't think this is actually about implementing type safety for your languages. It's about more.
Does it be a further?
Yeah, that would probably be something a bit different.
There is.
And then it basically introduces again these operations, but under the type classes now. So that way, these operations are actually generic over your expressions and other people's expressions and stuff. Lots of different types you may use inside your expression. By making substitution type class a multi-parameter type class, we have the flexibility and safety. Imagine a different declaration of type capital E, which contains both variables abstracting E and type variables abstracting type. An instance of subst E declares that E variables can be replaced with E's, and another instance subst typed E would declare that type variables can be replaced with types inside E's. Yes, I mean, at this point it's really just about, they made it really generic. That's what this slide is about.
Does anyone else want to
No,
drink or
thanks.
food?
Moving on a bit, because the previous section is a bit dry about that sort of stuff. The freshness monads, which maintain the freshness constraint, is important. Since the freshen operation relies on the generation of fresh name, operations which make use of it, such as unbound, must execute within a monad. The fresh type class shown in figure 10 governs those monads, which can be used for this purpose and is used to avoid tying users down to a particular concrete monad. The fresh class is quite simple. It requires a single operation, fresh, which takes a name as input and generates a new name based on a given name, which is guaranteed to be globally fresh in an appropriate sense. For example, a simple concrete implementation might keep track of a global counter, which is incremented every time fresh is called, appending a new counter to the given to the base variable name. However, this is unsatisfactory in many instances. For example, consider the simple pretty printer for the untyped lambda calculus in figure 11. If we pass the term lambda dash x dash y dash z, 2 at 0 apply to 1 at 0 apply to 1 0 at 0, it produces lambda x dot lambda y1 dot lambda z2 x applied to y1 and z2.
I have a similar complaint about if you look at so Haskell's deriving or maybe Template Haskell as well, I think. So if you look at the splices, then they'll have globally unique names, which end up becomes really hard to read because you've got these big long variable names.
Right. Yeah.
It's just kind of x and y, but it'll be x, 1, 2, 3, 4, 5, something.
Yeah. Yeah. Any sort of automatic system tends to do that. We can see here that numeric suffixes on y and z are unnecessary since the existing names do not clash, but the fresh operation does not have enough information to make this assessment. So I think that's sort of what you're sort of saying, is that this is fine, but then it does some stuff that's sort of unnecessary.
It's the easiest thing to do, right?
Yeah. And so therefore they also introduced this other type class called lfresh, which can generate locally fresh names. Lfresh works like fresh, but has more to go on. It avoids ends m allows us avoid ends m allows us to specify the names ends, which should be avoided by calls to lfresh in the subcomputation m. Unlike fresh, lfresh is not guaranteed to pick globally fresh names. It only guarantees not to pick names prescribed by an enclosing call to avoid. The intention is that it will return the argument unchanged when the name is not specifically to be avoided. So using lfresh, we can rewrite the pretty printer so that names are chosen fresh with respect to exactly those names currently in scope. To accomplish this, we need only to use lfresh instead of fresh, and lunbind instead of unbind, and lunbind generates names for the binder using lfresh, which then hands the body to the continuation route and the call to avoid. So I guess that's basically just a quality of life improvement. It's not fundamental to implementing this or making use of this stuff.
Although you wonder, are there situations where it might be a performance thing because you might be able to do things in parallel?
Yeah.
You don't have globally.
That does actually make sense. Could definitely do something like that. Parallel reduction, parallel evaluation, parallel optimization of different parts of the code.
You might want, like, speculating here, you might have things where you might want to inspect the transformations in between for some reason.
Right,
And
yeah.
if it goes and does a renaming of a bound variable,
Yeah.
you look and go, what? As a human, you look and go, what? What's going on here? Oh, and this avoids having that problem.
Yeah.
If inspecting it intermediates is a thing.
Well, that makes sense.
Like the dumping splices between the Haskell.
I'm not familiar with that problem.
So yeah, I guess you're out of the room, but then when you do that, the generated code has globally unique names, which are rather than single letter variable names.
Yeah.
Oh, in the Haskell, the core, the GSC core.
No, it's dumping out the surface level Haskell syntax, but it's got globally unique variable names. Generated.
Section 6.5 talks about being able to do unbinding not just for one expression, but two or more abstractions with the same fresh names. For example, in order to check the convertibility of two LF is a particular language dependent types, we must open them with the same fresh name and recursively check the convertibility of the bodies. I've never really used. I have used the LF a little bit, but I don't think I've ever really played the dependent type part. Well, maybe the whole entire language is dependent type. So.
I've seen the name, but I don't know anything about it.
Which operators is
This was back in type theory, when we had that session many years ago.
Oh,
Back
as
then.
in LF precursor to ELF precursor
Yeah.
to 12.
Oh,
Yeah.
like that. Okay.
So, yeah, for most people, they will not understand the motivation for this thing. But so
I thought you were saying that it's actually written in the paper.
Yeah, ELF is a logical framework.
yeah. So Unbound also provides an unbind to operation that allows us to open two related bindings. And it looks like what it does is just basically says bind is any of P1, bind is any of P2, make perm, just pi do freshen P1 return. I don't know what make perm is. Make permutation, maybe. So the function works by first matching the binding variables of the two patterns together to create a permutation pi. And then this operation will fail if the patterns bind different number of variables. Next it freshens the first pattern P1 and then use the result to open T1 and then T2. Finally, it must compose the permutation from freshening P1 with that from the match and use a new permutation to rename the second pattern. So that's cool. Yeah. So finally we get to sort of our conclusion and discussion. So that's probably not that important. There's camel style specifications, which is not important because nobody here knows about this thing, I'm guessing. Unbound in practice. So we've been using Unbound in the Trellis project in the context of type checking and evaluation of an experimental dependently typed language. In this context, Unbound support for telescopes is potential. I didn't talk about the section that talks about telescopes mainly because, again, like if you haven't ever worked with dependent types, it's sort of just doesn't make any sense. Our experience with Trellis has allowed us to find and correct a few bugs. For the most part, the use of Unbound has been unremarkable in the sense that it just works. The only drawback of using Unbound is the lack of pattern matching for abstract type binding. And since because Unbound is implementing generic programming, it will be slower than a hand-coded implementation. If necessary, we could easily replace the generic definitions of the hand-coded operations by overriding alpha-type class instances. I think I was in one of the, I don't know, Yao Lambda ones, and they were saying that you can use those rewrite rules to also improve certain generic operations as well. Do you remember? Like there's some rewrite things that you can apply.
If the speed is running the generic code, that's hard to see how you make that faster. That's kind of just a given. So they're talking about though, just putting this in your project, then it's going to just take longer to compile.
Yeah.
But I can't see why when you then run it, so you use this to write a compiler.
Yeah.
And then that compiler, I can't see how that would run slower.
Yeah. No.
So I don't know which, but when they say performance, which are they? Oh no, sorry, you're right. They're just saying it's hand coded. You can, you might be able to add some optimizations.
So this alpha type class has functions which have defaults given there's a generic constraint on the program generic chain or whatever data type you're using, but they're just saying if we actually wrote those manually, it'll perhaps run faster instead of going through the generic.
Right, and that's what you were saying about the rewrite rules.
Yeah.
Rogers. Yeah, sorry.
Yeah,
I
so
took a
there's
long time.
Yeah, so you might go through some X, because it's done generically, you might, to do a list, first of all we do it for an element, and then we use this function to go to a list, and maybe if you just knew it was list of ints, you could do a hand-coded thing which is faster, but if you did a rewrite rule that said something lists should be this, maybe you could get the same performance anyway.
Yeah.
That sounds.
So one thing that I think was concerning me was about how when you sort of build up your expression tree, you have to sort of go down the expression tree and rewrite those things and go back up again. I think this section is sort of mentioning that. It has performance concerns with respect to open and close. While the standard operations are linear in the size of terms, operations that are defined on a freshness window must open and close terms for each binding level, which could be expensive. So though we have had not any difficulties of this sort in Trellis, It is possible that larger programs and deeper binding depths, these operations can dominate. To mitigate this difficulty, Unbound supports an experts-only interface where critical operations can be written directly over the terms in a manner similar to our implementations like this.
So that's why the abstract types aren't actually abstract, they're
Yeah.
to expose.
Yeah. We have not explored the interaction of Unbound with standard optimizations. For example, caching free names, an implementation of substitution that can stop early if the name being substituted for is not cached. If we remove names from bound patterns which are preserved only for error messages, the locally nameless representation interacts nicely with hash consing, as all alpha equivalent terms have the same representation. We are also working on bringing our normal implementation up to date. And then we're using the else fresh mode. The nominal implementation can avoid freshening when unbinding patterns if the patterns are already sufficiently fresh. There are trade-offs involved. Alpha equivalents can be more expensive with the nominal version. One important contribution of Unbound is that it provides an abstract interface to name binding. Clients can write their code against this interface and, depending on their particular application, choose the most appropriate implementation. More importantly, our locally nameless implementation provides a simple reference semantics with this interface, and alternative implementations may use this semantics to prove their correctness. And then now it sort of goes back and sort of gives that history of locally named
I was just
representation.
going to say, sorry, before you get into that, did anyone go to Edward Kmet's talk at Lambda Jam last year? He gave a quite
No, I don't-
reasonably in-depth talk on the problem, like exactly the problems here, like particularly the performance. So when you, alpha renaming, and you have to kind of traverse into a data structure, and how you pass your context, like that becomes, if you're really trying to get a really fast performing compiler, that becomes a problem. And he was talking about different data structures to hold that context, and it seems like
What context are you referring exactly?
so it's still just implementing the lambda calculus.
You mean like the abstraction?
It's the environment effectively.
I think part of it was, so he was talking about renaming. He talked about a few different versions, and about how the context was actually represented as a data structure, to avoid. So if it's just a list, you have a kind of, once it starts getting big, it's quadratic, and you're kind of concatenating contexts and in various operations, and that becomes a problem. Yes, it's kind of interesting to think about this as an engineering problem.
Yeah. Are you saying context in terms of expression tree or context in terms of something else?
Just this name is bound to this expression, the usual content, like big gamma.
Right. Okay.
Yeah. It was just interesting.